Hey folks, can you hear me?
Yes.
Karen, your mic's not working. Jessica, your mic is muted.
Hi, Professor. I'm
Hear
here.
me?
Hello?
Yep.
Can you hear me? Hello?
Hang on. That might be my speaker.
Hello?
Okay, now I can hear you.
Can you hear me?
I can. Can you hear me?
Yep, I
Yeah.
can hear you.
Great. My speaker got unplugged somehow.
Oh
So,
yeah.
Karen, what can I do for you tonight?
It's only about question three that I'm having issues at. I
Question
don't understand how to go about it for question three.
on the special homework.
Yeah.
All right, I'm going to pin this and you're going to let me know if this focus is good. Can you see it?
We can see it.
Is it in focus?
Yes, it is.
Okay, great. Let's see if we can get it even better. Pretty good. All right. So can you read question three or shall I grab it? Maybe I should grab it.
So it says negative pi, find each set, use interval notation, use the union symbol if needed. The universe equals real number.
All right. So we're on special homework number 10, problem number 3. The universe is the real numbers. And we're supposed to try to find each of these sets as an interval. We want to calculate each one. So the first one is what? Square bracket negative pi, comma, 2 pi, and then what is it? A soft parentheses?
Soft parenthesis, union, bracket, pi, comma, 5 pi, soft parenthesis.
All right. So I think part of what I might be able to do to help you with these problems,
We can do just one. It's just to figure out how to go about it.
well, let's just make, yeah, let's make a number line. Let's draw a number line. Okay, a real number line. So here's the reals. Okay, so here's 0. Pi is about 3.141. So we'll put pi here, and this will be 2 pi. This will be 3 pi. This will be 4 pi. And this will be 5 pi. Do you agree? And
Oh,
then negative pi, negative 2 pi, and so on and so forth. So we're just multiplying, uh, we're just jumping by jumps of size pi. Like instead of having 0, 2, 4, 6, 8, 10, or 0, 1, 2, 3, 4, 5, we've got 0 pi, 2 pi, 3 pi, 4 pi, 5
yeah.
pi. Does that help?
Mm-hmm.
And I just want to make sure, yeah, the farthest to the left any of these go is negative 2 pi. So and the furthest to the right any of these sets go is 5 pi. So, do you remember what the union symbol means?
Yeah, it means that they're together.
It means or.
Oh.
So any x in this union is an x that is in this set or in this set or both, right?
Mm.
And so, in fact, we can draw several number lines and it'll be maybe easier to see the relationship between these different intervals. Like we can shade these particular intervals and look at what their union and their intersection turn out to be, okay? So for example, the set that starts at negative pi with a square bracket, comma, to 2 pi with a soft parentheses. What does the square bracket mean? Do you remember?
It means that it starts there.
That's right. And it includes that value.
Mm,
Like a closed hole, if we were drawing it with open holes and closed holes. So we'll put a
mhm,
square bracket at negative pi, and that means we're including negative pi. And it goes to 2 pi, but it does not include 2 pi. It just sneaks up as
stops there.
close as you want. Does that make sense?
Hmm.
And then it's also everything in between. And there's a lot in between here. It's not just negative pi, 0, and pi. No, no, no.
Hmm.
There are an infinite number of real numbers in that interval. Does that make sense?
Hmm.
And then this set starts at pi and includes pi and goes to 5 pi but doesn't include the 5 pi. So this one starts at pi and includes the pi, goes all the way out to 5 pi but does not include the 5 pi. So it's all of these numbers in here, including the pi, but not including the 5 pi. So when we are trying to calculate the union, we want the x's in the reals that are either in this set or in this set or both.
Both would be we can start as from negative pi to 2 pi.
Wait a minute. Are you talking about both or are you talking about the union?
Oh, union would be negative
Let's work
pi,
on the union first, and then we'll talk about the intersection, which is the elements that are in both. But right
um
now, let's finish the union.
negative pi to 5 pi.
That's right, because it starts here, picks up all of these, and then it picks up all of these. So you're right. It starts at negative pi and then it goes to 5 pi. Do we include the 5 pi in the answer?
Yeah. No, no, no,
Wait,
no. It's a
no,
soft
it's
bracket.
not. Right.
So that's what you want us to do on there.
Yeah, for all of them except the last one, you're going to have to use a union symbol.
Mm.
Let's look at the intersection. Jessica, is this helping you? Okay, Jessica may have stepped away. So Karen, now for the intersection of these two sets, we're looking for the real numbers that are in the first set intersect, that's and in the second set. Does that make sense?
Hmm.
We only want the real numbers that are in both of these.
It
Well, the
would be.
nice thing about drawing this picture and having it lined up
Hmm.
is we can, see, oh yeah, this is the overlap area, right?
Hmm.
Are we going to include the number pi?
Yeah.
Because pi is certainly in this one, and it's also in this one because we have a square bracket. So we're going to include the pi.
Hmm.
Are we going to, how far are we going to go?
We're gonna stop right at 2 pi.
Uh-huh. Are we going to include the 2 pi?
No, it's gonna be a soft parent cheese.
That's right, because the 2 pi isn't in this one. It is in this one, but that doesn't put 2 pi in the intersection. It's not in this one, so it's not in both. So
Mm.
you're right. So how would we write our answer?
Brackets pi, comma 2 pi's parentheses.
That's right. Set difference means we start with the first set and we subtract away the second set. Are you looking at the problem?
Yeah, I am.
So what is the part C? Can you read it to me?
Part C says that negative pi, a bracket, negative pi, comma 2 pi, soft parenthesis, minus bracket pi, comma 5 pi, soft parenthesis.
Great. So it means we're starting with this set. Negative pi, including the negative pi, up to, but not including 2 pi. We start with that and we subtract away any of the elements in here that are also in the second set. Well, we've already kind of indicated those overlap elements, right? Those are the ones we have to subtract away. Does that make sense?
Mhm.
Doesn't matter these, uh,
If we
you know,
subtract this, like we remove it, do we start as from 2 pi?
no, because 2 pi is not in this set. This set is the x's in the reals such that x is in the first set, negative pi square bracket to 2 pi soft parentheses, and x is not in the second set. So we have to throw away any elements from the second set. We have to take those elements away from the
From the
first set.
second set. From the second set.
So everything in this set has to be in square bracket negative pi to soft bracket 2 pi.
Pi.
That's what we're starting with.
Oh, and we're subtracting what we have. So it's gonna be like negative pi pi.
Y- Uh, let's see. Yeah, because what's left, negative pi is good because it's not in this set, so we don't have to subtract it away. Will we use a square bracket or a soft bracket?
It's gonna be a square bracket.
That's right, because it really is an element of this first set. And
Mm-hmm.
then we're going to go to where we start subtracting, which is at pi. Good. Now, the question is, are we going to include pi in this set difference or
No,
do we subtract it away?
it's gonna be a parentheses, soft bracket. Yeah.
Because we subtracted pi away from the second set because it lives in the second set. We
Mm,
subtracted it from the first set, but it lives in the second set. So that's very good.
okay, that works.
And don't these pictures help?
Yeah, it does. It
You got
does.
to draw
It's
a picture.
so
Yeah.
yeah, so simple that way. Because I was the thing that was confusing me was I didn't know that we could write pi this way, have 1 pi, 2 pi, 3 pi. I didn't know we could do this. So yeah.
Yep. You sure can. Because pi is just a number, but it's an irrational number with an infinite decimal expansion. We don't want to try to write it as a decimal because no matter where we stop, we have gotten an imperfect value for pi because pi goes on forever. It's
Mm-hmm.
decimal expansion. Now, what is the part D? Is it a complement set?
Yes, it's a complement set. It says bracket negative 2 pi, comma 2 pi, soft bracket complement.
So I've made up a new set.
Yeah.
All right, so let's draw this set and then we'll think about the complement. Remember, this is the reals minus this set, square bracket, negative 2 pi to 2 pi soft bracket. The complement is everything that's outside of this
Of
set.
it.
So it's all the reals that are left after we subtract this set. Does that make sense?
Everything left after we subtract the sets.
Yeah, after we subtract this set. Because by definition, the complement of negative 2 pi square bracket to 2 pi soft bracket, the complement of this set, we want to take the complement. So we want to understand that this complement is any x in the reals such that x is not in this negative 2 pi square bracket to 2 pi soft parentheses.
But if it's outside, how do we say it's outside? Is it gonna be like
It'll
uh
be all of
right here
these
and the other
forever
side?
and all of these
So
out to
how,
the right. And then we have to think about the endpoints.
so will it be like negative infinity to negative 2 pi or I
Yeah,
don't know.
this right here is negative infinity, which is always a soft bracket, to the negative
Negative.
2 pi. Now the question is, do we want a square bracket here or soft
It's gonna be a
parentheses
square
here?
bracket.
If we put a square bracket, we're saying that negative 2 pi is going to be in this green set.
Oh, so
Isn't
what?
negative 2 pi in this set?
No,
And we
it
have to,
is though.
so we have to take it away.
Oh, yeah, so it's not anymore. Soft
So it,
brackets.
yeah. And then union,
Oh,
all right, because we have to jump
oh.
over. So the,
Okay, yeah.
right,
Because I was, how are we gonna write it? Because
with a
it's around the
union, because it's
middle.
anything that's in this side or over on this side.
Okay.
So now we have to figure out how to write this green set that goes off to the right.
It's gonna be soft bracket 2 pi to comma infinity soft brackets.
Now I'm going to ask you about why did you say soft bracket? You're saying that you don't want
Because
to have 2 pi in this complement?
I mean actually on here actually um it has a soft bracket on the other side, so I
Yeah,
think
2 pi is not an element of the set.
mm-hmm.
It's not in here. 2
So I
pi is
should include
not
it.
in here. So it will be in the complement.
Oh, but what isn't the complement because it was not included earlier?
Yes, we don't have to subtract it away because it wasn't in this set to begin with. See, it's like that's a soft bracket there, but this is a square
Mhm.
bracket here going that way. Does that make sense? Because these have to complement each other. One will be soft and one will be square when
Yeah,
we're taking the complement. Does that make sense?
yeah, drawing the line just makes it more easier overall to understand.
Well, and since this one was square, we have to throw it away. So that's why this one was soft.
Hmm. Okay,
Good
that works.
question.
That works. That works.
Jessica, do you have a question?
Yeah, I did have a question on one of the homeworks. Let me just pull it up.
Is it WebAssign?
No, it's homework 10 was one of the problems.
Did you watch the video from last night?
I was in it. I was in the video, or I was in the Zoom last night.
I know. So,
Mm-hmm.
okay, so I wonder what this one is that we didn't
So now we went over the
cover.
partitions
Yeah, we covered
in
partitions.
6.
Remember last night
Mm-hmm.
we took this finite set A and we took these subsets A1, A2, A3, and we asked if that collection A1, A2, A3 is that a partition of A? And it's this collection of sets, A1, A2, A3, is a partition of A if each element of A appears exactly once in one of these. And you don't want any element to appear twice, and you don't want to skip any elements. Each element of the big set A must appear exactly once in exactly one of these for it to be a partition.
Mm-hmm.
And these properties, like when we intersect any two of these together, A1 intersect A2, or A1 intersect A3, A2 intersect A3, and checking that those intersections are empty, that's where we're verifying that no element of A appears twice. And then when we look at the union of A1 union A2 union A3, and when we see that that union is all of A, then we're checking that every element of A actually does appear in one of these. See what I mean?
Yeah.
That's the intuition behind the partitions where the big set's just finite. And it's the same with even interval notation partition ideas is every element in the big set that's getting broken up, each of these elements has to appear in exactly one of these sets and you can't miss any of them. Each of these has to appear, but it can only appear once. It has to appear exactly once. Does that help you?
Yeah, I think it was more so number three, because I know we went over like examples using partitions. It was just more so number three, I would say. On the homework,
Problem
special
three
homework.
is the problem we just did. Problem three is the problem. Are you looking at homework
Gosh, with the
10?
negative pi. Okay. Okay.
Yeah, that's not partition. That's just finding the union and the intersection and the set difference and the complement where the sets look like, intervals.
Yeah. And then number six, I know we went over last night, and four and five are pretty similar to that one. I would say, I guess, can you kind of just go over number two in that case? I didn't have any questions on the web assign.
Yeah, but I don't want to give the answers to
God.
those. I've already given the answer to one problem tonight.
Or a similar example?
Yeah, I'll make up a similar example. I'll call it 2 prime.
Okay.
So it's a little different. All right, so let's let A be this set with 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, here's collection 1. It's going to be A1, A2, and A3, where A1 is going to be the set with 3, 6, and 9 in it.
Hmm.
A2 is going to be the set with 2, 4, 6, and 8 in it. And A3 is going to be the set with 1 and 10 in it.
Wait, I'm so sorry, ma'am. Can I see the other paper real quick? Um, for the compliment, because I didn't finish writing it.
Why don't you see if you can think of it, think it yourself right
No,
now?
no, no. I already did it. It's the line. I already have the answer. It's the line that I'm drawing. The way you draw it on the paper is the line. Okay, zero. Two. Okay, okay, that works. Thank you. That was all.
Okay. So let's look at this collection. You know, is the collection a partition of A? If so, verify each property. There are 3 of them of a partition. They're in the notes, and I also wrote them last night in our office hour notes. Here's the 3 properties of a partition.
Isn't it each element? Oh
And
no.
if not, explain why some properties fail. So to check if it's a partition, each element of A has to appear exactly once in only one of these sets for that collection of sets to be a partition. So what do you think? Does every element of A appear in one of these sets exactly once?
Yes. No, actually.
What's
Not
missing?
it's missing five. It's missing seven.
That's right.
So just five and seven.
So no, 5 is not an element of the union from I equals 1 to 3 of these A sub i's. 7 is also not an element of the union from I equals 1 to 3 of the A sub i's. In other words, if you union up A1, union A2, union A3, 5 is not going to be in that union. That means 5 is not in any of these, and neither is
Mhm.
7. So this is property 3. Property 3 fails. Is there any other property that fails?
Um,
Here are the properties. These
yeah.
are all non-empty, so property 1 is good. How about the pairwise disjoint? Are these sets pairwise disjoint from each other? In other words, if you take any two of these, like A1 and A2, and intersect them, is that intersection empty? Is AI intersect AJ always empty? Or is there some overlap between A1 and A2?
Uh, there is overlap.
Yeah, what is the intersection of A1 and A2?
They intersect at, is it six?
That's right. So property 2 fails because the intersection of A1 and A2 is the set with the element 6, and that is not empty. And the I is not equal to the J because 1 is not equal to 2. We really took two different sets and they both shared an element. And so there were two reasons it fails to be a partition. Does that help?
Yeah. And then are you able to just scroll up so I can just see the set of numbers?
It
Perfect.
was, yeah, the set from 1 to 10.
That's it. Okay.
But you should refer to class notes
Mm-hmm.
for the definition of partition.
Yeah, I remember you had wrote it in yesterday. It was saying given a set A in subsets A1, A2,
So it's
so on.
yeah, or you can take a screenshot of that if you want.
Mm-hmm. I have it right here on my phone.
Fantastic. Do you
Mm-hmm.
have other questions? I think that, just understanding what the intuition is behind a partition, every element of the big set appears
Mm-hmm.
once and only once in one of these. It can't appear twice, it can't appear in two of these, and you can't miss any. Okay?
Okay.
That's the intuition. I mean, that's what these rules mean. The first rule just says when you're building these AIs, don't make any of them empty because that's just silly to have a partitioning subset that's empty. It doesn't do anything for you. The second property says none of these partitioning subsets share any elements. They're all pairwise disjoint. And this one says each element in A does appear in one of these. That's what this union means. Is if you union A1, union A2, union A3, that union should give you all of A back. Does that help?
Yeah.
Great. Do you have another question?
I know we have about 30 more minutes left. I know you did say we have a test coming up soon. So I guess if we can just kind of work through some practice problems just to kind of prepare and just slowly kind of get ready for that test.
Yep. We have test 3 coming up, and this is definitely, part of test 3. Proofs by induction are a part of test 3.
Mm-hmm.
How about we look at some of those induction proofs from the homework number 8?
Okay.
Or 9. I guess it was
Um,
homework 9.
Nine. Okay.
Yeah, let's work through some of
And
those.
then I have nine
Oh,
put up on my side
and were you
too.
able to use the formula to find the sums? Did I give you, Jessica, let me see.
Yeah,
Is
the
your Is your homework 9 grade posted yet? Oh, here's yours.
Let me see.
Oh, actually, there's an issue. Here, I'm looking at yours. You have to see me after
Mhm.
class. No, you use the formula just fine. Let's look at, it looks like you did fine on number 1. You did okay on number 3. You did okay on number 4. All right, let's take a look at this question. So we're going to prove this statement for all integers n greater than or equal to 0. So this is our P of n, okay? It's that 10 divides 11 to the k plus 1, whole thing
Mhm.
minus 1, okay? It's a divides problem. Uh, for the proof by the PMI, we're just going to
Okay.
let P of n be as above, okay, because we can see it. And on our basis, what should we say for the first statement of our basis? We're trying to get on the bottom step of our staircase to heaven. So our n naught is always given to us, and it's 0. So what should we let n naught equal to?
Um, we write what we want to
We always start the basis by telling the reader where we're starting, for what integer we're starting
show.
yeah. So what is our n naught? It's our lowest level value
So I thought
of,
the next line is we want to show.
well, we'll write we wish to show in a minute, but we don't know what we wish to show until we know where we're
So that 10
starting.
is equivalent to 11 k plus 1 minus 1.
We're just trying to figure out
Or
where
just to
this,
let n know. So let n know be an integer.
just let it be 0. Wherever we say prove it for all integers n greater than or equal to whatever
Okay.
is here is the starting point. That's our first integer for which we're going to prove it, okay? So here we're going to let n naught equal 0, okay? That's always your first sentence in the basis proof is you identify the
Okay.
value of the integer n, we usually call it n naught, the first one,
Hmm.
where we're starting things off. And you're always told where to start things off. So this is our first sentence. Now, what do we wish to show in the basis? We want to show we're standing on that bottom step. So we wish to show P of what is true. Well, it's always that first value. We're starting at the bottom here. We wish to show P of 0 is true. Does that make sense? Are you there? Jessica, what's happened? Are you there? Well, then log out and log back in, okay?
The screen is frozen.
Well, mine's not, so log out and log back in. You may be having some internet issues.
Yeah, the screen's just frozen.
Well,
Yeah,
then
can you hear
log.
me?
Yes, can you hear me? Can you hear me? Yes, you can.
There you go. I can hear you now.
Hi.
Okay. I'm back. Hi.
All right. So we're always told where to start the argument, and that
Hmm.
that number is our first value. It's
On the
like
number
it's
line, yep, because it
yeah,
goes
we're going
in
to
of
try to get
zero and
on
of
step
one.
zero. So we're going to try to prove that we can stand here on the bottom step, okay?
Okay.
Now, what is the statement P of zero? Let's notice P of zero says 10. Oh, this isn't right. This should just be a K. 10 divides 11 to the zero. Oh, this should be an N. It's got to be, we just put a zero in for N. 10 divides 11 to the zero minus 1. Do you see how this is P of zero? If this is P of N, P of
Hmm.
zero means we just put a zero in where there's an N, okay? Are you with me?
Yeah.
So that's what we have to prove.
Okay.
So we wish to show, these can all be thinking notes. Well, what does it mean to say 10 divides 11 to the zero minus 1? What's the definition of divides? Let's recall. X divides y if and only if y is equal to x times some integer m. In other words, y is a multiple of x. That's what it means to say x divides into y. So if we want to figure out that 10 divides into 11 to the 0 minus 1,
Hmm.
our x is 10, but our y is 11 to the 0 minus 1. So what we really wish to show is that the y, which is 11 to the 0 minus 1, is equal to a multiple of 10. Does that make sense?
I'm just taking it in. So, okay, so people said 10 equivalent. And then how we're getting from the first line of 10 is equivalent to the second line is what again?
The definition of divides,
Okay, so once we put that definition in, that's how we're getting that line.
x divides y. It's denoted like this, x with a vertical line y. And what it means is our if and only if. It means that y is equal to x times a whole number. Like if y is 12,
Hmm.
3 divides 12, right? Because 12 equals 3 times what integer?
4.
4, right.
Hmm.
But 5 does not divide 12 because if x is 5 and y is 12, you can't solve the equation 12 equals 5m and get an integer m that'll make 5 times that integer equal to 12 because 5 doesn't divide into 12. See what I mean?
True.
So
Okay.
when we are saying we want to show if this is P of n and we know P of 0 is what we get when we just plug in a 0 for the n, we want to show 10 divides into 11 to the 0 minus 1.
Hmm.
What do we really wish to show? Well, it means 10 has to be a divisor. In other words, 11 to the 0 minus 1 has to equal 10 times some whole number, some integer. That 10 really fits into 11 to the 0 minus 1 a whole number of times. Does that help?
Yeah.
10 is our x. 11 to the 0 minus 1 is our y. So when we change it to an equation, and we always want equations, we always want to change our definitions into equations. So the y, which is the 11 to the 0 minus 1, gets on this side by itself, and it has to equal the x, which was 10, times some integer.
Gotcha.
Got it?
Mm-hmm. I just made the note now in my notes.
Yep. So do tell. We know what we need to do. This is our
Hmm.
wish. We wish to look at 11 to the 0 minus 1, and we want to somehow show that it looks equal to 10 times some integer. All right?
That's our overall thought with the cloud.
Uh-huh. This is our wish. This is just the basis step. We haven't even gotten to the inductive step yet. We're just trying to get on step 0 of our stairway, you know?
Okay.
So how are we going to show that 11 to the 0 minus 1 is equal to a multiple of 10? Well, let's look at 11 to the 0 minus 1 and see what it actually looks like. You ready to observe?
Mm-hmm.
All right, so what is 11 to the 0 minus 1, Jessica?
0 minus 1.
Well, it starts with knowing what 11 to the 0 is.
True.
So what is 11 to the 0?
It's either 11 or it's going to be 0.
Here's a fact.
Oh, because anything to the 0 I thought is 1.
Yes, for any
Mm-hmm.
non-zero real number r, r to the 0 is always 1.
Yeah.
So 11 to the 11 is just a real number. It's not 0. So 11 to the 0 is what is it again?
1, anything, because anything to the 0 or anything to 1 is 1.
Not anything to 1. 11 to the 1 is 11.
Okay. But
But
anything to the
the
0
0 is 1. So
is
this
1.
is 1 minus this 1. So what is that?
So 1 minus 1 is just going to be 0.
And now our job is to show that 0 is equal to 10 times some integer, right? Because we want to
Hmm.
show now that 10 divides in 0 into 0, because 11 to the 0 minus 1 turned out to be 0. So we
Hmm.
want to somehow write 0 is equal to 10 times some integer. Well, what integer will work?
Um,
What can we multiply times 10 to get this 0?
0.
That's right.
Hmm.
And this copy of 0 is an integer. And that's the definition of divides. That means 10 divides 0. But 0 is 11 to the 0 minus 1. So 10 does divide 11 to the 0 minus 1. So 10 does divide 11 to the 0 minus 1 by the definition of divides. And we just proved P of 0.
Hmm.
See, because that's what we wanted to prove is P of 0. We just did it. So now let's go to our induction step or our inductive step. What's the first sentence that we should write in the inductive step? You know how we started our basis step by telling our reader what the first value of n naught is or of n is? We said, oh, by the way, let's let this n naught, this first value of n, be 0. We want to show P of 0. Now, in the inductive step, we have another
Just
variable we're going to introduce. Do you remember what it is?
K? Is this where we say like assume
Yeah,
or
let
let
K
K
be some integer
that belongs
where
to?
where does K need to start?
It will start at 10. 10 is equivalent to
No, we want to start, we want to
P.
see, we want to prove we can get off this zero step. You know,
Okay.
we're at step zero. We want to be able we're going to wish that we can step up to the next step. So we start our K at the bottom where we just proved we're actually standing there at the bottom.
Okay, so we start
And
at 0 then.
yeah, we got to introduce K. K starts at 0 or 1 or 2 or whatever wherever we're told to start our proof, that's where K will start. And now we do assume something. What should we assume? What's our inductive hypothesis?
Assume.
We want to show that we want to assume that we're standing on step K. So like if we're way up here on the ladder, we might be down here, but we just assume we're standing on step K, right? We assume we're there, and then our wish is going to be to step up to step K plus 1, okay? That's our wish, is to get up here to the next step. But
Okay, so then,
we assume we're standing on the Kth step. So we
hmm
assume P of K is true.
so it's P of K. Okay.
All right,
hmm
i.e., now let's actually write what that statement P of K is. Well, you can see P of N up here. So what is the statement P of K going to be? And we're going to write it down explicitly.
Sorry, you
Every,
said what is the what going to be?
what we want to write P of K. It's called our inductive hypothesis. It's the assumption we're standing on step K, of this staircase, right?
hmm
So this is P of N. The N is called the argument. Here, the K is called the argument. So to find P of K, we just look at P of N, and everywhere we see an N, we just put the K. So can you read to me what P of K is?
P of K, it
I'm
would
just going to use
be
this.
10 is equivalent to, so assume 10
No, 10 divides
divides. Divides 11K,
11 to the K.
11 to the K minus 1.
Good. Now, let's change that into an equation using the definition of divides. Remember, in our wish for P of 0, the wish was that 10 divides 11 to the 0 minus 1, but that's not a very helpful wish. We wanted to change it into an equation because equations are always like our proof money. So we wished 10 divides 11 to the 0 minus 1. That meant we wished that 11 to the 0 minus 1 was equal to 10 times an integer. Okay, that's what it means to say 10 divides 11 to the 0 minus 1. Remember?
hmm
It means we can multiply uh, 10 times a whole number. Like this is just a bunch of copies of 10, maybe 5 of them or something, who knows? Turns out to be 0 copies, but whatever, it's still an M.
hmm
But now we want to do the same game and translate this statement about divides into the corresponding equation, which is the definition of 10 divides 11 to the K minus 1. So what equation will we get that states 10 divides 11 to the K minus 1? In the same spirit that we changed 10 divides 11 to the 0 minus 1 into this equation, we want to do that for this statement. 10 divides 11 to the K minus 1.
Would we start off with, because if we were changing it, would it be like 11? We started off with 11, correct?
Mm-hmm.
So 11K, so you switch to 0 on the K, minus 1 equals 10 M. because that's going based off of our wish. For some integer m.
Right. This is now our inductive hypothesis.
Okay.
This is our money in the bank. We're going to use this induction hypothesis. This is what we have in our hand because that's what we're assuming. We're assuming that 10 divides 11 to the k minus 1. So we are assuming that 11 to the k minus 1 is a multiple of 10. Good. You following everything?
Mm,
So now let's write our wish. We wish to show what? We assume P of k. What do we wish to show?
um, wish to show.
We assumed we're standing here on step P of k.
Right, it's because we have to go to the k plus 1. So we want to
Right.
show 10 divides 11k plus 1 minus 1.
Great. Let's change it to an equation because to show this, we're going to have to show that there's an equation that holds, i.e., we wish to show what equation holds.
Okay.
You tell me.
Um,
It's going to be like what we did here and
mhm.
what we did here. And now we're looking at our wish again.
So would it just be 11k plus 1? We want to just show that equals 10p.
I'll just use P. See how that's our wish? We want to show that 10 divides into 11 to the k plus 1, whole thing minus 1. So this is our wish. This is our money, but this is what we're trying to get, is it this equation. So basically, we want to say something smart about 11 to the k plus 1 minus 1. We want to show that this, when we start with this expression, that we can turn it in to 10 times an integer. Okay?
Hmm.
And we'll be able to use this proof money along the way. But again, changing a statement about divides into the corresponding equation that the definition of divides gives us is the right way to use the definition of divides when it comes down to doing the algebra. And now we're getting into the nitty-gritty algebra. This is what we have to show.
Okay.
All right, so we'll keep our inductive hypothesis where we can see it, and we'll keep our eye on the prize. And we'll also have to show that P is an integer. And it'll be like sums and products, or maybe sums and differences or something of integers or integers, okay? So now, this is a little different than all our formula proofs by induction because it's more of a statement, but it's an equation we're trying to show. We'll start with this, the left-hand side, and we'll turn it into the right-hand side. So we're going to look at 11 to the k plus 1, whole thing minus 1. And we're going to try to work on it and break it down until it turns into 10 times an integer. You with me?
Hmm.
All right. So what is the first step in breaking this 11 to the k plus 1 minus 1 down? Well, it's kind of not obvious,
Separating.
separating, because the way to kind of get a clue as to what kind of work you need to do to break it down right is look at the proof money. We know we want to use this equation. To use this equation, we just need to see an 11 to the k, just one of them. This is 11 of them. We just want to see one copy of 11 to the k minus 1. So we need to somehow extract an 11 to the k out of 11 to the k plus 1. Do you know how to do that?
Will we start with just like either 11 or 11k?
Yeah, I'll say 11 times 11k, right? Because this becomes 11 to the k plus 1 because there's a 1 there, right?
Yeah.
All right, the whole thing is still minus one. We don't want to lose our minus one. Great. And now there was a trick I showed you in class. We're trying to get some tens. Well, we got too many 11 to the k's. We got 11 of them. We only want one. To use this equation, that's just one copy of 11 to the k minus the 1. So, well, this 11, can't we rewrite it as 10 plus 1?
Yeah. But
And
would it
now,
be,
mhm,
or would it be like 10 something? Could you can write the 10 by
10,
itself?
no, it's 10 times 11 to the k
Okay.
plus 1 times 11 to the k. But what is 1 times 11 to the k?
One, no, 11?
It's just 11 to the k.
11 to the
Like
K.
1 times anything is just that anything, right? 1 times a pumpkin head is a pumpkin head. All
Okay.
right. So
Hmm.
when we multiply anything by 1, we just get that anything back and we still have that minus 1. Now we're in good shape because we have extracted an 11 to the k, one copy of it. We still have this minus 1. Ah, our inductive hypothesis was an 11 to the k minus 1. Now we see that here, see?
Hmm.
So I can put like green brackets around this to indicate this is going to let us do the inductive step. The 10 times 11 to the k can just come down, okay? But we can make the substitution, which is when we say by induction. The reason we say by induction is because we're getting ready to use our inductive hypothesis. What is 11 to the k minus 1, according to our assumption? Because we assumed this was true.
10 times 11, K plus 1.
Yeah, well, yeah. What is this 11 to the k minus 1? What can we substitute in for it according to,
It's not 0.
well, what does this say 11 to the k minus 1 is equal to?
Oh, 10M, 10M. So we just plug 10M in.
Right, that's our inductive step where we used this equality to make this substitution. Do you see it?
Yeah.
Remember what our prize is. We're trying to factor tens out of 11 to the k plus 1 minus 1. See, we started with the 11 to the k plus 1 minus 1 right here. We're trying to get it looking like 10 times an integer. Well, let's keep going. What can we do now to get this 10 out front?
You do 10 parentheses 11. 11, it's either K or M.
It's
Okay,
11 to the
11K.
k
Okay. And
because
then
this
just
is
plus M.
10 times 11 to the k.
Mm-hmm.
So we pulled the 10 out and it leaves behind the 11 to the k. Now, what about this factor? When we factor out the 10, what's left behind?
So then plus M and then close parentheses.
Great. And this is going to turn into our p, which is going to have to be an integer, right? We have to verify that that is. So what do? We use the fact that m was an integer, and we know k is an integer. So we say, since k and m are integers, p equals 11 to the k plus m is an integer because what? What operations are we using to build 11 to the k plus m? What arithmetic operations are involved there? Well, there's addition being used, right? Because there's a plus sign between the m and the 11 to the k. And raising 11 to the kth power is just
Hmm.
shorthand for multiplication. It just means 11 times 11 times 11 times 11 dot 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 times 11 for a total of 10 factors of 11 multiplied all together. Did I say 10? I meant k. K factors of 11. And multiplication of integers produces integers. So in fact, 11 to the k plus 1 minus 1 is equal to 10 times p, where p is an integer.
Mm-hmm.
And that means 10 does divide 11 to the k plus 1 minus 1 by definition of divides. So
And then I should write that p is an integer, right? That you have in red.
yeah, because
Okay.
that we had to prove p was an integer. We didn't just write it, we proved it by invoking the fact that addition and multiplication of integers produces integers. That's why p is an integer.
Okay.
And we started with k and m. Of course, we know 11 is an integer. It's not a variable, so we don't have to say that. But if you wanted to say, since 11, k, and m are in z, then this p that's built from 11, k, and m using addition and multiplication is also an integer. It's in z. So in fact, we started with our induction hypothesis, p of k. Remember, we assumed p of k, and that was this proof money.
Mm-hmm.
From that, we prove p of k plus 1. We prove that 10 actually divides 11 to the k plus 1 minus 1 after assuming that 10 divides 11 to the k minus 1. So p of k does imply p of k plus 1. What we just showed is if we're standing on step k, that in fact we can step up now and
Okay.
stand on step k plus 1. That's what the inductive step is all about. It's about stepping up, being able to climb the staircase. See, this whole induction thing, we want to get on the bottom step, and then in the inductive step, we show we can climb the steps. So that means we can get on the staircase and we can climb forever and ever. And that's the last sentence. By the PMI, invoke the PMI, by the principle of mathematical induction, now we know we can climb that staircase forever. So we can say P of n is true for all integers, no matter how big they get, n greater than or equal to 0. So this goes to infinity. This will be true forever and ever, no matter how big the n gets in this statement. It could be 11 to the 300,049 minus 1, and that will still be a multiple of 10. Because we've proven we can climb the staircase. And once we're on step k plus 1, we've proven we can climb to the next step, k plus 2. I mean, we've proven we can just keep climbing forever.
Okay.
I'm going to stop the recording and I'm going to turn off chats because I want to just talk to you for a minute.
Okay. And I'm still writing down just